Okay, so today we will have a quick introduction to quantum mechanics from the point of view that we will be using it in quantum computing. So I will, of course, not be going into detail, but I will try to give a comprehensive review of the fundamental axioms or postulates of quantum mechanics, from where the quantum mechanics the application can be understood in different areas. And along the way, while we are discussing the basic postulates of quantum mechanics, we will of course be specializing all of those postulates to a two-level quantum system, which is a qubit, because we are building this formalism towards understanding of quantum computing. So I will be taking examples of qubits to sort of explain the postulates. So the idea is this, that in this lecture, you not only become familiar with the basics of quantum mechanics, if you're not already familiar, but you also get an idea that how quantum mechanics postulates are used, in building a framework for understanding quantum computers. So let me start sharing my screen. And as always, you are welcome to ask questions at any time. You can just unmute yourself and start speaking. Okay, so let me pull out my tablet. So today, we will have an introduction to quantum mechanics. And since our focus is on quantum computing, examples will be taken so that we understand two-level quantum systems, which we now call qubit. Okay, so quantum mechanics was developed in the last century, especially in the earlier part. And if we go into the history, the development of quantum mechanics was essentially forced upon physicists when some of the new phenomenons like photoelectric effect or black body radiations and behavior of subatomic particles like electrons couldn't be explained using the classical physics of Newton and Maxwell. And initially, the development of quantum mechanical ideas was ad hoc. Okay, the first quantization, postulate from Planck, and then another postulate from Bohr in the form of quantization of angular momentum of electron in hydrogen atom, and many other, postulates that were introduced. For example, de Broglie's wavelength of small particles moving at a certain velocity. But later on, people tried to develop a theory that can we explain all of these different, assumptions, like the existence of quantum of energy, like photon, or quantization of angular momentum, and many other postulates. Can we develop all of this, from some fundamental axioms or fundamental postulates? So then, with many hits and trials, people were able to zero in on a few postulates that if we assume them to be true, then we can, drive all the myriad effects and implications for small particles for quantum systems. So in this lecture, I will review those postulates, and there is some debate still as to whether if there is two postulates, if they can be derived from another one, and so on. We won't be going into that. We will discuss four fundamental postulates that we think that can be used to derive everything that is, useful in physics and to describe theories. And before I go into describing, these postulates, let me say that these postulates themselves is not a physical theory, but these quantum mechanical postulate or quantum mechanics, so to say, provides a mathematical framework which you can use to develop new theories or describe other physical theories and so on. But in itself, it's not something that tells you about the physics or about some theory, some fundamental theory. Okay, so let's discuss these postulates, and I will discuss them one by one. Postulate number one, and let me label this postulate as a postulate that has a name, and let's call it state space, and I'll explain it a little bit later. So this postulate says that with every physical system, with every physical system or quantum mechanical system or isolated quantum mechanical system, you can assign a vector space, actually to be more precise, a Hilbert space. So a Hilbert space is a collection of vectors which are all normalized, and we also have an inner product defined for those vectors. So this is a collection of vectors. Now each physical state of the system, let's say you have some system, let me just give it as a pendulum. So this pendulum can have different physical states, and this first postulate say that each of the physical state of this pendulum can be described by a state vector in this vector space, and this vector space is called a state space. So this is the first postulate, and this vector space in general is a complex vector space, that the vectors can have complex numbers as components. Okay, so let's just discuss a few implications of this postulate. And for that, let me take an example of a two-level system. So for a two-level system, let's say we have a system where there are two possible states that the system collapses to when we measure it. So remember, this is an important thing. When we say two-level system, it doesn't really mean that it has only two possible states. It means that when we measure it, and I'm going to come to the measurement postulate later, it collapses to either of these two states. But in general, system can exist in infinitely many states, because the state is a linear superposition of these two basis states. So essentially, a two-level system is a system that has two states in its basis, which means that each and every other state can be described as a linear superposition of these two basis states. So for a two-level system, the state can be described by this state ket A0 plus B1, with one important restriction, and the restriction is this, that A mod square plus B mod square must be 1, that the state is normalized. And we'll see shortly again as well that this normalization requirements come from the probability conservation when we discuss the measurement postulate. Okay, so let me now say a few more things about the state space of a two-level system. Now, these A and B are in general complex numbers, that it has a real part and an imaginary part. Similarly, B has some real part and some imaginary part. So in general, there are total of 4 real parameters that describe the state psi of a two-level system. So it means that we can, easily use a geometrical, representation to represent the state, because there are 4 parameters. But fortunately, these 4 parameters are not all independent because of this restriction above, that a mod square plus b mod square is 1. So essentially, we have 3 parameters three real parameters that can be used to uniquely specify the state of this 2-particle system. And which means that, one possibility is this, that you can think of this x, y, and z coordinate system, the real 3-dimensional space, and maybe you can specify each point. You can relate one of the points of this 3D space to each state of this 2-level system. But this, first of all, is a 3-dimensional picture. And we also have to make sure that the parameters keep satisfying this a mod square plus b mod square is equal to 1 condition, which means that parameters only lie within a certain region. And then it's not, easy to geometrically visualize it because it's a 3-dimensional space. So people have developed, a bit simpler picture to geometrically represent the state of a 2-level system, and it's called a block sphere. And let me show how we can represent the general state of a 2-level system on a block sphere. And this actually exploits one other thing that we'll shortly discuss. And let me go back to this state psi. So in general, we have written it like this, that this a and b are general parameters. But since a is a complex number, b is a complex number, it means I can write this a as some r1 exponential iota theta 1 in polar coordinate. Or actually, let me call it some exponential iota some phi 1. Similarly, b can be written as some r2 exponential iota phi 2. Because each complex number, can be written as in terms of its magnitude and in terms of its phase. So now if I put this a and b here, this becomes r1 exponential iota phi 1 0 cat plus r2 exponential iota phi 2 1 cat. Now we can take exponential iota phi 1 common, and I'm left with r1 0 plus r2 exponential iota phi 2 minus phi 1 and 1 cat. With the condition that we already know is that r1 square plus r2 square is 1, because this r1 is the a mod and r2 is the b mod. Now let's call this number phi 2 minus phi 1 as some other number phi. And since r1 square and r2 square, they always square and add to 1, it means I can represent this r1 and r2 as either cosine of some angle and sine of some angle, or sine of some angle and cosine of some angle, because we know cos square of some angle plus sine square of some angle of the same angle is always equal to 1. And let me define that angle to be theta by 2 plus, and this now exponential iota phi 2 minus phi 1 is written as exponential iota phi, and this is sine theta by 2. And it will become clear soon that why we took theta by 2 instead of just theta. So this is now the state of a 2-level system, and you can see that we only have now 3 parameters. There's phi 1, there's theta, and there's phi. Using these 3 parameters, I can uniquely specify this state phi. And we will see later that when we try to find the probability of measuring this state, and of course, when we measure this state, it's either going to collapse to 0 or 1. which means that for this system, we can measure the probability of finding 0 or 1. And when we try to compute probabilities for this two-level system, this global phase, it's called global because this is an exponential iota something, which is multiplying the whole state. So such a factor is called global phase. It's just a word for this. So this global phase doesn't play a role because when we will be computing probabilities, we will see that we have to multiply with complex conjugate, and complex conjugate of exponential iota phi is exponential minus iota phi, and when you multiply, this factor goes away. So it means that up to the global phase, I can represent the state of a two-level system by only two parameters, and these parameters also have a certain range. For example, this phi is anywhere between 0 and 360 degrees, and 360 degree is also written as 2 pi. And this theta by 2 is anywhere between 0 and 90 degrees, which means that theta itself is anywhere between 0 and 180 degree is equal to pi. So it means we now have a two-level system state, which is represented by two parameters, phi and theta, where phi is anywhere between 0 and 2 pi. And it is between 0 and 2 pi because this phi comes in this exponential phase, and this exponential iota phi, let me just write this definition for those of you who might have forgotten it. So since this exponential iota phi is just cosine and sine, and cosine of an angle between 0 and 2 pi is the same as between 2 pi and 4 pi and so on. So it's a periodic function. So beyond 2 pi, you simply come back to the same point. So that's why phi only has to be between 0 and 2 pi. And this theta by 2 has to be between 0 and 90 because this number is a positive number, this number is a positive number. And since we wrote R1 as cosine theta by 2 and R2 as sine theta by 2, we have to make sure that theta has a range such that both of these numbers remain positive, because R1, R2 are the magnitudes of the complex numbers A and B. So this can remain positive only if this theta by 2 is between 0 and 90. And this can remain positive only if this theta by 2 is between 0 and 90. So that's why there are these ranges for these parameters, and theta by 2 is between 0 and 90. So it means theta is between 0 and pi. Now, we can represent it in many ways. You can also, represent perhaps on a real space, on a real plane. For example, you can take theta as an x-axis, phi as an y-axis, and your theta goes from 0 to pi, and your phi goes from 0 to 2 pi, and you can assign each point within this rectangular area to the state, to one state of the two-level system. This is all real numbers are possible, so there are infinitely many states in this present in this region. So this is one way of representing, but there's a more intuitive or a better way that helps in visualization the states of two-level system in a better way, and that is that we represent it on a sphere. Because on a sphere, the magnitudes of any vector that goes to the surface of the sphere is fixed. So if we have a unit sphere, so that its magnitude is always 1, it means that we're able to satisfy this condition all the time, that R1 square plus R2 square is 1. I mean, it's already encoded there. And the second is that we can use the angle with, let's say, the z-axis as theta, which represents our parameter theta. And if we take its projection in the xy plane, the projection of this vector, and then call this angle between the projection in xy plane with the x-axis as phi. Now, since for each point on this sphere, this phi can only go from 0 to 2 pi, and theta can only go from 0 to pi. All the ranges are automatically satisfied if we are on this unit sphere. And that is actually the most common way that is used by people to represent the state of a two-level system. But remember, it's not a physical picture. Whenever you see a block sphere and we say, okay, the state is like this, or the state is like this, or the state is like this, there's nothing physically that corresponds with this picture and the state of the actual system. Because if we have implemented the qubit as a superconducting, nonlinear oscillator, it's just different energy levels and the state of the system as a superposition of those levels that we are talking about. There's nothing physically, moving in any direction. So just keep this thing in mind, that this thing is just a geometrical and intuitive aid that helps us understand different operations. Okay, so according to postulate 1, each physical system can be, described by a complex vector space, which has an inner product defined in it, and we call that vector space a Hilbert space. And only the normalized state vectors represent the state of the system. Now, for a two-level system, we require 4 real parameters, but because the magnitude has to be 1 always, we really only need 3 real parameters. But since when we are talking about probabilities of measurements, the global phase doesn't play a role. So up to the global phase, and I emphasize it, up to the global phase, we can describe the state of a two-level system by a point on the unit sphere. And this unit sphere is called the block sphere. Okay, so let me take a pause here and see if you have any question about block sphere. Abdullah, you are able to get it? Ji Ahmed Kirbani, you have a question?
Sir, ये जो phi determine करने के लिए आपने projection की है, ये xy plane पे की है?
हाँ जी, xy plane पे की.
अच्छा, सही है.
That's how it's normally done. So whenever we talk about, angle theta, theta is the angle of this vector with the z-axis, and phi is always usually the angle that is made by the projection of this position vector in this xy plane with the x-axis. Okay, that's the convention. Okay, and now you can see that why I took theta by 2 instead of theta over here. Because if I had taken theta, that theta would have to vary between 0 and 90. And instead of using the full sphere, my state could only be described by either the upper half sphere or the lower half sphere. And to have, to use full sphere for visualization purposes, we chose theta by 2 over there, so that our theta can vary from 0 to full pi. Okay, any questions? Any other questions?
Sir, एक दफा repeat कर देंगे कि block sphere के जो angles हैं ये किस तरह हमने define किए हैं, मतलब कि projection इसकी किस तरह हुई है?
Okay, so let me draw the block sphere again. Let's say this is the sphere, and this is the xy plane, and you imagine an imaginary cross section of the sphere at the xy plane, and let's say this is some point on this sphere, and its position vector is this. Now the angle of this vector with this z-axis is parameter theta, and if I project this vector onto the xy plane, this will intersect the xy plane somewhere, and this intersection makes some angle with the x-axis, so we call that angle as phi. Okay.
Okay, sir. Thank you so much.
All right, so let me just represent a couple of states on this system, and you will get a better idea. For example, if my state is just this zero state, where does it show, on this block sphere? And if you compare it with, this general formula, sine theta by 2 exponential iota phi 1, you see that if this has to equal to this, theta by 2 must be 0 degrees, because if this is 0, cosine 0 would be 1 and sine 0 would be 0, so this will go away. So this means that theta is 0 degree. So any point that has theta 0 degree represents this cat 0, and this actually is, and phi doesn't matter, because whatever phi is, since it's multiplying with 0, so phi is not important. So this is this vector, this block vector represent the state cat 0. Similarly, if you want to see where state cat 1 is, so you will obtain this 1 if your theta is 180 degrees, because when theta is 180, sine 180 by 2 is sine 90, sine 90 is 1 and cos 90 is 0, so this goes away. And now phi also is important. If sine 90 is 1, phi must be 0, right? If phi is 0, then exponential iota 0 would be 1. So this vector has this position. So a downward vector is this vector 1. Similarly, let's say if we have this special vector, this is called a plus vector for obvious reason, because this can be written as 0 plus 1. Let's see what is the value of theta and phi for this one. And if I write it like this, 0 plus 1 over under 2, 1. So this immediately tells me that phi has to be equal to 0 degrees, because exponential iota phi, if it would be, other than 0, I might be getting either minus or something else or some iota. So phi is 0. Now theta has to be 45 degrees. No, 90 degrees, sorry. Because if theta is 90 degrees, then theta by 2 would be 45 degree, and cos 45 is 1 over under root 2 and sine 45 is 1 over under 2. Now where is this vector theta 90 degree and phi 0? This should be this vector, this plus vector that I wrote, because for this vector, you see this angle is 90 degree, and since this vector is already along x-axis, its projection in xy plane is again going to be this along x-axis, and the angle between this green vector and x-axis is 0. So this plus vector is represented like this. Let's take this another vector, minus vector, 0 minus 1. So for this, again, theta is 90 degree, because theta by 2 is 45 degree, and this 1 over under 2 factor is coming with both. But now phi is going to be 180 degrees, so that exponential iota pi is minus 1 because of this minus sign over here. So this minus vector is this vector right along the negative x-axis, because this is a vector whose phi angle is 180 and its theta angle is still 90 degrees. So the vector along x-axis is plus vector, and the vector along minus axis is minus vector. And by the way, these plus minus vectors also form a basis for this two-level system, because you can check that these plus and minus vectors are normalized, and you can check the dot product plus minus 1, and this is 0. So they're orthogonal. So any two vectors that are orthogonal and they are normalized, they can form a basis for this two-level system. So this is another basis. Okay, we will see that this is sometime is called a Fourier basis in one-dimension case, or Hadamard basis as well. Okay, similarly, you can work out the position of other vectors. All you have to do is, if you have, general vector, for example, something like this, you are given like psi is equal to some iota 0 plus 1 minus iota 1, and of course there is this some factor m which is dividing so that the vector is normalized. Now if you want to find out theta and phi, all you have to do is put this is equal to a and put this is equal to b, and find their magnitudes and their phases, and from there you can find theta and phi, and you can work out for general cases as well. Most of the time we don't actually have to worry about this. Just some canonical representations would suffice. And by the way, just as an example, if the vector along negative y-axis and the vector along positive y-axis, they also have special name, plus iota and minus iota, and you can easily check that plus iota vector, this is just a name, and this is 0 plus iota 1, and minus iota state 0 minus iota 1, and they also form another basis, and there are actually many more bases that you can construct. All you have to do is make sure that the vectors are orthogonal. Now you might have already started noticing one thing. When we talk about the real 3-dimensional or 2-dimensional space, our orthogonal vectors had a 90-degree angle between them. Okay, because if you see my finger and this pen, they are at 90 degrees to each other and they are orthogonal in real space. But on the block sphere, you see that orthogonal vectors have a 180-degree angle. Okay, for example, this 0 state and 1 state are orthogonal, but there is a 180-degree angle between them. Similarly, this plus state and minus state, they're orthogonal, but there's 180-degree angle. And that is simply because this block sphere is an artificial construct that we have constructed to visualize our two-level systems for our convenience. So don't be confused, or don't try to relate it to any physical geometry of the states. That's my point of emphasizing this thing. Okay, so let me summarize postulate 1 again, that each physical system has a state space associated with it, and each point in the state space represent a physical state of the system. And notice that this postulate doesn't tell us that for a given quantum mechanical system what that state space is or how you can find a state space. It doesn't bother about that, because that is something that depends on a problem, and it varies from your consideration. If you are taking into account only mechanical forces or electrical or electrodynamical or and so on, what types of interactions what you're including, how many states your system can have, and so on. So that is something for different disciplines to figure out. But this fundamental postulate is powerful enough that it gives us sort of a starting axiom that whenever we have to describe a physical system, we need to look for a Hilbert space to which its physical states correspond. And this is a completely different viewpoint than Newtonian physics, right? In classical physics, each state of a physical system corresponds to a certain position and a certain velocity in 3-dimensional real space. But this doesn't say anything like that. This is, first of all, your Hilbert space is complex, and it's continuous, and there's no mention of velocities or positions and so on. Okay, so let's now move on to the second postulate. So postulate number 2, and this postulate deals with evolution of state or change of state it tells us how the state of the system should change. For example, you have a given Hilbert space, like and there is a certain point of the Hilbert space which represents to a certain physical state of the system, and you want to see that how the system goes from one state to the other state. Or if you're talking about a two-level quantum system like a qubit and up to a global phase, if you want to figure out that if your system is at a certain state, how does it go from, let's say, from this to this state? So how does it move from one point to the other point on this block sphere? And this postulate tells us that the state of the system changes under some transformation u from psi to psi prime in such a way that the state remains normalized. That when we started the evolution, the state was normalized, which means that the inner product of psi with itself is 1, that it has a magnitude 1. So what we require is that after the evolution of this closed, we're talking about the evolution of a closed system, a system which is not interacting with something else, should be 1. Okay, and this can happen only if our transformation u is unitary. And I'm not going to show it mathematically, but I'll show it if u is unitary, then this happens, but you can show it in the reverse order. So this will happen only if u is a unitary transformation, and since we can represent transformations with matrices, so this is a unitary matrix. A unitary matrix, by the way, is a matrix whose complex whose conjugate transpose, which is transpose and conjugate combined, is equal to u inverse. So a unitary matrix is a matrix. If you take its transpose and take its conjugate, it is equal to its inverse. So second postulate requires that all transformations have to be unitary, because such a transformation would preserve the norm of the state vector, which also means that the unitary transformation would make sure that when your system is starting, a two-level system is starting at a certain point on the block sphere, after transformation, it remains on the block sphere and it doesn't fly away either outside or inside. It doesn't go here or it doesn't go here. It's not allowed under this postulate, because a unitary transformation will preserve the norm that before the transformation it has this magnitude 1, and after transformation it has magnitude 1. And we can easily see that if u is unitary, this can happen. Okay, so let's see mathematically. So if psi ket is u psi prime bra, I can find it by taking the complex conjugate of this u psi. This is called dagger. So this dagger will when it comes to psi and it comes to this, so psi dagger is nothing but psi, because this column vector goes to a row vector with its elements conjugated, and this is this u. Now let's find the inner product of these two. So we will have psi prime and psi u dagger into u psi. Now if this u is unitary, it means that this u dagger u must be identity, because this is inverse of u. So this is identity. So identity goes away and this is psi. So it means whatever was the norm of the state vector before unitary operation, it remains the same after unitary operation. This is equal to. So only unitary operations are allowed on closed system. And this is actually very important because our quantum gates are nothing but operations on physical quantum system. And since postulate 2 is telling us that only unitary operations are allowed, all of our quantum gates from now on have to be unitary matrices. So this is, one important condition on our matrices, that the complex conjugate and transpose of unitary matrices must be equal to U inverse, which means that all of our quantum gates are going to be unitary. As an example, if I take the X gate, so X gate was described by this 1 0 1 1 0 matrix, which we last time wrote like this, right, in outer product form, because when I apply this X gate to state 0, I get 1, and when I apply this X gate to state 1, I get 0. So this is like a classic NOT gate, right? Because this 0 state goes to 1 and 1 state goes to 0. So if you want to write its truth table, so this is input, this is output. So 0 goes to 1 and 1 goes to 0. And you can check that this X is unitary. And let me quickly do that. And let me actually do two things. First, let me check if X is unitary. And for that, if I take the transpose and conjugate of X, so 0 1 1 0, its conjugate will give us the same thing because there's no iota. So no iota, no chain. And when I take transpose of 0 1 1 0, I still get 0 1 1 0. So this is actually even better, that X conjugate transpose is X. Let's now see if X is its own inverse or not. So X into X would be 0 1 1 0, 0 1 1 0. So 0 into 0 plus 1 into 1, 0 into 1 plus 1 into 0, 0 1. So this is identity. So it means X square is identity. So X is, first of all, a unitary matrix, and second, its inverse is X itself. So when I apply X twice, I get the same state before. So X gives me whatever is here. If there's some state alpha, I get alpha back. Now let's try to picture the operation of X gate on the block sphere. So let me make the block sphere over here. X, Y, Z. Suppose you have state 0. So when I apply X gate, you apply X gate, the state becomes 1. And this is as if the X gate rotates your input state by 180 degrees. So X gate can be viewed, in two ways. One view is, your classical view from a classical computer, that X is a NOT gate. Okay, 0 goes to 1, 1 goes to 0. But another, sort of operational view on quantum system is this, that on the block sphere, it rotates the state vector by 180 degree. Now rotation have to happen around some axis, and though it's not clear from the 0 1, but we can see in a moment that this rotation is in fact around x-axis, which means that if you have some state over here, which makes some angle over here and some angle over here, this state is rotated around x-axis by 180 degrees. So it goes from here to this side. So if this is x-axis, the rotation is around x-axis by 180 degrees. Whatever, if it is 0, it goes to 1. If it is some combination of 0 and 1, after rotation, it goes by 180 degree to the opposite side. And we can actually see if the rotation is around x-axis by applying x to the general state ket psi. So suppose psi is cosine theta by 2 0 plus exponential iota phi sine theta by 2 1, and if I get psi prime by applying x to psi, this is the same as cos theta by 2 1 plus exponential iota phi sine theta by 2 0, because this 0 becomes 1 and this 1 becomes 0. Now I can, take this exponential iota phi common, and this becomes sine theta by 2 0, because I want to get it back in this way so that I can find angles after rotation, after this x operation. And I have exponential minus iota phi cos theta by 2 1. And since in my standard form 0 comes here and 1 comes here, so when I took exponential iota phi, I brought this term over here and took this term over here, and this exponential minus iota phi wasn't present here, so I put exponential minus iota phi. Now exponential iota phi, this sine theta by 2 can be written as cos theta plus pi by 2, and this exponential minus iota phi can be written as exponential iota, pi minus phi, because exponential iota pi would actually 2 pi minus phi, and this cos can be written as sine theta plus pi over 2. Now this is our new angle, and this is our new theta. So theta goes to theta plus pi, and phi goes to 2 pi minus phi, or phi goes to minus phi. And let's see if this is a vector. Before we apply the x gate, it has some angle theta, and its projection has some angle phi. Let me clean it a little bit. Actually, let's just draw a new one, because we can quickly do that. So this is the vector with theta and phi before rotation. Now after operation of x, theta has to go to theta plus pi. So this is theta plus pi would be rotation by pi degrees. So this gets to the other side, and when it gets to the other side, it's angle phi becomes, instead of phi, it becomes minus phi in the opposite direction. So what has happened, that theta has changed by pi degrees. So theta is the angle with the z-axis, and phi has gone to minus phi. So whatever was on this side has gone to that side. So it's a rotation around x-axis. Okay. All right. So let me take another important gate, and it's a Z gate. This is also a poly gate. So this was 1 0 0 minus 1, and I leave it to you to check that this is also unitary, that Z conjugate transpose is again Z, and Z square is identity. You can check that. And since this Z can be written as 0 0 minus 1 1, if I apply this Z to state 0, you see if 0 comes from the right side from here, this 0 into 1 would be 0, because these are orthogonal. So this term goes away, and 0 into 0 would be 1, and I will be left with 0. So a Z gate applied to 0 state will give me 0. Similarly, if I apply Z to state 1, let me work it out for you. So this Z gate is in outer product form like this. Now this one multiplies here and this one multiplies here as well. So this 0 into 1 is 0. So this term goes away. This 1 into 1 is 1. And I'm left with -1. So the Z gate doesn't do anything to state 0, but to state 1, it adds a minus sign. And this minus sign is essentially iota pi, exponential iota pi, because cos pi is -1. So this is called a phase flip gate as well, because for the state 1, it adds a phase term exponential iota pi. On the block sphere, we can check its action by applying this Z gate again to your general state psi. So general state psi is cosine theta by 2, 0 plus exponential iota phi sine theta by 2, 1. So Z to 0, nothing. So cos theta by 2, 0. And Z to 1 is -1. So this becomes minus exponential iota phi sine theta by 2, 1. So this minus sign can be converted to exponential iota pi. So this becomes exponential iota phi plus pi sine theta by 2, 1. So this means that the Z gate doesn't do anything to theta, because cos theta by 2 remains cos theta by 2, sine theta by 2 remains sine theta by 2, but phi is changed to phi plus pi. So if I look at the block sphere, and I have some general state with some angle theta and its projection making angle phi with x-axis. After applying this Z transformation, this state rotates in such a way that theta remains theta. So it means that the state is going to be on this cone, and phi becomes pi by phi plus pi. So this is angle phi. So from here it goes to the opposite side, the projection. So the actual vector is over here. So it means the vector rotates around Z axis by 180 degrees. So this is the Z axis, this is Y axis, this is X axis. So Z gate rotates a state ket around Z axis by 180 degree. The X gate rotated the state ket by 180 degree around X axis. Okay, you see this point?
Sir,
Say 180 for both.
Sorry, but can you please repeat the question?
So the X gate is rotating around the X axis by 180 degrees, and the Z gate is also rotating around the Z axis by 180 degrees.
Okay, so your voice was cutting out, but if I get your question, you are asking the angles of rotation by both gates. So x-axis also rotates the state ket by 180 degree, but it rotates around x-axis. Similarly, Z gate also rotates state ket by 180 degree, but it rotates around Z-axis. We just saw that theta doesn't change. So it means rotation has to be around Z-axis, because theta is the angle with Z-axis. So if it doesn't change, it means the rotation is taking place with around Z-axis. But phi changes by 180 degree, which means the rotation is by 180 degrees.
Thank you.
Okay, good. Now, I'm not going to, discuss here in detail, but this is something that you should work out, that the Y gate similarly works just like X and Z gate, but this rotates by 180 degree around the Y axis. And this also, is very similar to X gate and Z gate, and they all satisfy this thing. And these are important things to remember, that many times, when we will be building algorithms using these gates, we will have to use these properties. And let's say if we are applying Z gate at somewhere, and if we want to get back to the original state, we can apply the Z gate again, and Z is its own inverse. Similarly, Y is its own inverse, X is its own inverse, and so on. And by the way, these properties are now very easy to remember, because you see X gate rotates by 180 degrees. So if you apply X gate again, you rotate by another 180 degrees. So total rotation becomes 360 degrees, which means that you did nothing. So you should get back to the same place. Similarly, Y is a rotation by 180 degrees around Y axis. So if you apply Y twice, the total rotation is 360 degrees. So you get back to the same point where you started. And same is the case with the Z gate. Ji Ahmed?
सर तो क्वांटम मैकेनिक्स के जितने भी गेट्स हैं, अगर आप उन सबको ट्वाइस अप्लाई करेंगे तो यू विल गेट बैक द इनिशियल स्टेट.
No, not all gates. There are only few. And I'll just discuss another one. Okay, let's discuss that actually. And let me discuss this S gate. This is also an important gate. So this is 1, 0, 0 iota. First of all, before you write any gate, you have to make sure that it's a unitary gate. And now I am writing this 1, 0, 0 iota gate. It's a unitary gate. You can check it. And it's very easy to check, because first you compute this S dagger, which is like you take the conjugate and transpose. So if you do this, you get this. And now, first of all, you see that this is not equal to S itself. But if you multiply this S with S dagger, 1, 0, 0 minus iota, 1, 0, 0 iota, you can check that this is identity. So this is a unitary gate. Now let's see what this gate does. So in the outer product form, I can write this gate at 0, 0 plus iota 1, 1, because this is at a position of 1, 1, this is at a position of 0, 0. Now, if I apply this S gate to state 0, let's see what we get. 0, 0, iota 1, 1. So apply to 0, nothing happens. But if you apply this to state cat 1, you get iota times 1, which is exponential iota pi by 2. So this essentially adds a 90-degree phase to state 1. Let's not see what happens if I apply this to the general state cat psi. So S applied to cos theta by 2, 0 plus exponential iota phi sine theta by 2, 1. Now when S goes to 0, nothing happens. So this is cos theta by 2. And when it comes to 1, it adds this phase. So I can collect this phase with phi. So exponential iota phi pi by 2 sine theta by 2, 1. So you can see the action in on the block sphere, that it's a rotation around Z axis, but by pi by 2 degrees now, because angle theta doesn't change and phi changes by 90 degrees only. So from here you go to this place. So from here the rotation is only by 90 degrees, because this phi changes from here to this place, so that 90 degrees. So in the XY plane, the projection rotates by 90 degrees when you apply this S gate. So your actual state vector goes from here to here, and the projection changes by 90 degrees. So this gate rotates only by 90 degrees. So it means intuitively you can think that S4 should be identity. That if you apply S gate 4 times, nothing is happening to theta every time. Phi is changing by 90 degrees each time. So after 4 rotations of 90 degrees, you should get back to the same place. And actually it is. You can actually check it by matrix multiplication as well. You multiply S 4 times with itself, you will see that you get to identity. So this is a gate that it's not its own, inverse. Okay, Ahmed?
Okay, sir.
Okay, so this is called phase gate. This S gate is the phase gate. Okay, so there are actually many other single qubit gates. And these single qubit gates are essentially some physical operations on a two-state system, which corresponds to rotations on the Bloch sphere. But before I move on, let me discuss one last single qubit gate, which is one of another, very important gate. It's called Hadamard Gate, and this is h square root 1 1 1 minus 1, and I leave it to you to check that it's a unitary gate. Okay, you can check that, and all you have to do is just compute h dagger and multiply with h, and you will see that it is identity. And actually, since -1 appears only in the diagonal, you can check that h dagger is essentially equal to h, which means that just like h square is also equal to identity, and h is its own inverse. But let's see what h does to state cats. And whenever you encounter a gate for the first time, always first think about its action on basis states 0 and 1, the computational basis states, and then you should think about the action on a general state psi. Okay, keep the general state a little bit for later. So let's work out the action of h on 0, and there are two ways to do it. Let me do it in both ways for your practice. So one way is this, that I use matrix form. So this is the expression for h gate. For 0 cat, I can write 1 0. So it works out to 1 into 1 1 plus 1 into 0 0. So this is 1. 1 into 1 is 1, minus 1 into 0 is 1. So this is 1. And this 1 1 vector can be written as 1 over under 2 1 0 plus 1 over under 2 0 1. And this is nothing but again 0 cat, but this is 1 cat plus 1 over square root 1. So this is 0 plus 1. So this is a state, by the way, that we already gave a name to, that this is a plus state. So when you apply Hadamard to 0 state, you get the plus state. Similarly, using the matrix notation, you can check that when you apply the Hadamard gate to 1 state, you get 1 over under 2 0 minus 1 state, and this is labeled as negative minus state. And by the way, you can check these things using the operator form, because this h 1 over square root 2 1 1 1 minus 1 can be written as 1 over under 2. This 1 corresponds to location of 0 0. This 1 corresponds to the location of 0 1. This 1 corresponds to the location of 1 0, and this minus 1 1 1. So you can work out the operation of this h, let's say on 1 state, like this as well. So 1 comes here, so 0 0 1. 1 comes here, this 1 on the right, 0 1 1. 1 comes in front of here as well, so plus 1 0 1, and at the end as well. Now using orthonormality, this is 0 because this is the inner product of 0 and 1 state, and 0 and 1 are orthogonal state. So this goes away. So this is the product of 0 and 1. This goes away. This is product of 1 and 1. Since these are normalized state, this becomes 1. This is product of 1 1. This becomes 1. So we are left with 1 over square root 2. This is 0 state minus 1 state. So you can work in matrix form, and you can work in using the outer product representation of operators. And you will realize soon that when we go to multi-qubit, it's much easier to work with outer product form than matrix form, because using matrices we quickly grew in size, simply because of tensor products. We saw at the end of last lecture that to represent multiple qubits, we need to prepare the tensor product state, and that exponentially increase the number of terms in your matrix when you go when you increase the number of qubits. Anyway, so this is minus state. Let's visualize the impact of this Hadamard operator in the block sphere. Sorry, my drawing is, oh my god, this is happening again, which means that I hope not much is lost. This somehow keeps crashing. Does anyone of you know a better option for using on XP tablets? Than Windows journals? Okay, so for now it appears that not much has been lost. Okay, so let's see the action of this Hadamard gate on the block sphere. X, Y, Z. So it means if you have
The screen is not shared.
Yes, thank you. So I need to reshare it. Okay, so let's say we have 0 ket and we operate Hadamard gate on it. So if I operate Hadamard on 0, so this translates to plus state, so it means I get to here. So the Hadamard gate brings us from 0 to this 1 state. So it means it's a rotation by 90 degrees, sort of around y-axis, because your 0 state goes to this plus state. Now if we have this 1 state, this goes to this negative state. So this goes from here to here. So what happens that the 0 state comes to the xy plane along x-axis. The 1 state also comes to the xy plane along the negative x-axis. Let's see what happens if we apply the Hadamard gate again. So if I apply Hadamard to minus state, and minus state is nothing but 1/√2, 0, -1. So Hadamard to 0 is plus state and Hadamard to 1 is minus state. And if you put back the expressions for plus state, for plus is 1/√2, 0 plus 1, and minus is 1/√2, 0 minus 1. Now if we collect it, this becomes 1/√2, 1/√2 half. Similarly, 1/√2, 1/√2 half. So half is common. So I'm left with 0 plus 1 minus 0 plus 1. So this 0 cancels away. There are 2 1s. So at the end, I'm left with 1. So Hadamard and minus state gives me 1. So it means that if I apply Hadamard gate to this minus state, it brings me back to 1 state. Similarly, if I apply Hadamard gate to this plus state, I go back to the 0 state. So essentially, this Hadamard can be used to switch between bases. That if you are in this 0, 1 basis, you can apply Hadamard gate and you go to this plus minus basis. And if you are in plus minus basis, you apply Hadamard, you go to 0, 1 basis. And by the way, this 0, 1 basis is called computational basis, simply because our classical information is in 0 and 1s, and we have labeled our two-level systems also in such a way that the two states that the system collapses to after measurement is also 0 and 1. So this is the most common basis that we use when we are working on computer. So it's called computational basis. This plus minus, can be labeled as Fourier basis in one dimension. Okay, so any question? If not, Abdullah Ahmed, you have raised your hand.
Can you hear me?
Yes, yes.
सर मेरा ये सवाल था हैडमार्ड गेट के बारे में ही जिस तरह आपने बताया कि कंप्यूटेशनल बेसिस पे हम हैडमार्ड गेट लगाते हैं तो हमें प्लस माइनस बेसिस मिल जाती है एंड वाइस वर्सा। तो इस केस में फिर हमारी रोटेशन क्या बन रही है जनरल केस के लिए?
Okay, so when we talk about changing the basis by applying Hadamard, then we don't talk about rotations. We talk about rotations if we stick to one type of basis. For example, if we are on the block sphere and we are in we have expressed our data in 0 and 1, we can talk about how the vector changes. But there is actually another way of talking about this rotation if we talk about change of basis. For example, if you have several qubits and your data is something like this. For example, this represents 0, 1, 1, and if you apply Hadamard to each of these data, so you essentially transform everything to along. For example, the 0 goes to +1, this 1 goes to -1, this minus state, and this 1 goes to minus state again, and this is plus state. So sort of we we make a 90-degree rotation, but we get back to the XY plane. And if we apply Hadamard gate back here again, we get back to representing our bits in up and down sort of position. So this is one way of visualizing, and we will actually make it more precise when we talk about Fourier transform in general dimension.
Thanks.
Thank you. So is there any question about postulate 1 and 2 before we move on to postulate number 3? So let me share the second node because I'm worried that the first one might run into trouble again. Okay. So let me summarize postulate number 2 again and its impact on quantum computing. So postulate 2 prescribed the sort of are the types of operators or operations or transformations that are allowed in quantum mechanics, and that was that all of these operations have to be unitary operations. And the reason is to preserve the norm of the state vector. And we saw its implication for two-state systems, which are qubits. And the implication is this, that different types of operations or quantum gates that we call them, they essentially amount to different types of rotations on the block sphere. So that's also one reason that some people actually describe quantum computing as sort of classical computing with an added part of rotation. Rotate, compute, rotate, compute. Some people, and compute here means the classical computation, that essentially you do some operation, you rotate your states, you do some operation, you rotate your states, and so on. And that's how you keep evolving your qubits. And the reason is this, that all these unitary operations, they essentially amount to rotations. The difference is this, that when we are in two-level system, we can imagine these rotations on a sphere. But of course, for multi-level quantum systems, we still call them rotations because they preserve the norm of the state vector. But of course, it's harder to imagine them in geometrical sense, that what those rotations look like. Fantastic. So we are now ready to go to the third postulate of quantum mechanics. Postulate 3, and it's called measurement postulate. And actually, this is a bit more complicated in general sense, but I'm going to give a simplified version for you people to understand. So essentially, this postulate means that the measurement process of a quantum system, it can essentially be described by a measurement operator. And let's say this is some operator m sub m. And the probability of measuring some state m is given by the norm of this state cat m upon psi. For example, your system is in some state psi, and you want to measure its state. So since you have a finite number of states in a quantized system, you have finite number of operators, and you to do that measurement, you apply the measurement operator to your state, and then you measure the norm of this operator. And this operator m is not unitary. Okay, so this is a non-unitary operation. So it means that the probability of measuring this label m is given by this, the norm of this new state vector psi ket. And since this m is not unitary, it means that this is not always going to be 1. Okay, we know that before measurement, the state was normalized, but our measurement operator is not a unitary operator. So after measurement, this is not guaranteed. So in general, we will have a number between 0 and 1. Okay, so apologies, this has collapsed again. And let me save the previous one and open the journal again. Okay, so I saved the previous file and I have now opened it again. All right. So we were talking about postulate 3, which is the measurement postulate, and it says that each measurement corresponds to a non-unitary operator mm, and if you start with your system in some state psi, you apply this operator and you get to state psi prime, and the probability of measuring this label m that this operator corresponds to is given by the norm of this state. Okay, and just to give you an idea, suppose you are in some state A0 B1 and suppose you want to measure the probability of finding your system in state 0. So let's say we have a measurement operator defined by this matrix 1 0 0 or 0 0. So let's see what's the probability of measuring your system in state 0. So we have to compute this inner product where this psi prime is 0 0 applied to A0 plus B1. So this 1 into 0 is 0. So 0 into 0 is 1. So I'm left with A0. And the probability, the norm of this state vector is 0 conjugate A0, because when I take its, convert this into Bray state, so I take its conjugate transpose. So this is complex number, it becomes conjugate only, and there's 0 Bray cat transpose to 0 Bray, and I inner product with A0. So this becomes A mod square 0 0. So this is a scalar number A square. This comes out of this inner product, and since this 0 is normalized, so 0 0 is 1. So probability of measuring system in state 0 is absolute A mod square. Similarly, you can construct an operator to measure in state 1, and probability of measuring your system in state 1 is B mod square. And you can check one thing quickly, that probability of measuring your system in state 0 and state 1 is 1, because the state was normalized before measurement. A0 plus B0, we required it by postulate 1 to be normalized. So that's why probability of measuring it in 0 and probability of measuring it in 1 is equal to 1. This, by the way, also means, as a trivial fact, that if I add both of the operators for measuring in state 0 and for measuring in state 1, the answer is identical. So the measurement postulate essentially gives us the physical significance for these parameters A and B, that we required them to be related in certain way, that the magnitude, the inner product of the state is 1, but now we have a physical significance attached to these numbers A and B, that their modulus squares gives us the probability of measuring the system in state 0 and state 1. Okay, is there any question about postulate number 3? Okay, so we have one more postulate, and that postulate number 4 deals with composite systems. And let me defer it to tomorrow, because tomorrow I will discuss multiple qubits, which are multiple quantum systems, and then we will complete our discussion of quantum mechanics by discussing the postulate number 4, and then going on to develop the formalism and quantum gates for composite system. But for today, let me stop here at postulate 3, and with just one quick note back to when we were describing the state psi in using 2 parameters only. We said that we can neglect this global phase exponential iota phi 1, and now you can see why, because this phase is multiplying this part and this part, and when we try to find the probabilities of measuring the system is either in 0 or 1 state, then this part goes away. You can argue that when we have this single qubit, even this part will not tell us about the probability of measurement in 1. That's correct, but we keep it still there, because when we prepare superposition state or we transform states from one to another place, this relative phase plays a part then. So we cannot ignore this, but this global phase, can be ignored when we talk about the measurement process. There's one other comment on measurement, and that's actually extremely important. And that is that suppose that you have a quantum system in some state psi, and it's not easy to actually find that state. It's extremely hard. The reason is this, that if we have a system in psi, we don't have access to A and B directly. When we measure, we only find probabilities which are A mod square and B mod square. So let's say we have a million identical systems that we have one system that we prepare in the same state 1 million of times, and then each time we try to measure the state, we either get 0 or 1, but sometimes we get 0, sometimes we get 1. So we can try to get the idea of A mod and B mod by plotting, let's say, a histogram. So for state 0, and let's say for state 1, suppose 30% is the probability of finding the system in state 0, and 70% is the probability of finding system in 1. So 700,000 times you found the system to be in one state, and 300,000 times out of the million you found it to be in state 0. So by plotting these histograms, we are able to still find only A magnitude and B magnitude. We have no information about, first of all, this global phase, and also about this relative phase. But we can, to get this relative phase, we can play some trick. And that is that before I measure, sometime I measure it as it is, sometime I do some transformation. Let's say I apply some Hadamard Gate and I change to another basis and then do a measurement there. So by doing these types of transformations, I can find this relative phase. But still, this global phase will not be found even by these transformations, because all of these transformations will be acting there, and this global phase is still going to be out of reach for this single qubit system. Which means that characterizing the quantum state of a quantum system completely is extremely hard and sometimes impossible. But we can always find the relative weights and relative phase of these basis states by doing measurements in computational basis, and by transforming to some other basis and then doing the measurements in that basis. And by collecting all of this data, we can sort of prepare the map of the quantum state of a quantum system. But still, we cannot characterize it completely, because our measurement apparatus is not giving us access to the state vector. It's not giving us access to them. It's only giving us access to the probabilities of measuring system in different, eigenstate or basis states of the system. And that also, only statistically. And in individual measurements, there's no way of telling if the system is going to collapse this basis state or that basis state. That's completely probabilistic. Okay, so is there any question on three postulates?